Okay, this video is going through section 2.3. 2.3 is continuing to multiply polynomials. However, it's going to talk about a couple special cases. So we're going to look at a couple patterns. If you are just comfortable multiplying polynomials using FOIL or distribution, the thing I want you to understand is you really just can use that. If you can identify these patterns, then we can do some shortcuts. They will also help us when we start to go backwards and factor instead of multiply. So let's just look at a couple of these patterns. Again, we want to be able to add, subtract, and multiply polynomials today, including special cases. So finding the square of a binomial. The square of a binomial, right, we can think about as just having like the square of a number. So if I'm looking at the number 3, I'm going to write this off to the right, times 3, I would just write that as 3 squared. And remember, when we have something squared, that just means that there are two of them. Now, if we look down here, this has 3x plus 5. 3x plus 5 quantity squared. That means that there are two of them. That is the same thing as 3x plus 5 multiplied by 3x plus 5. Okay, so again, we could just distribute this. 3x multiplied by 3x gives me 9x squared. 3x times 5 gives me 15x. 5 times 3x is also 15x, and 5 times 5 is a positive 25. Now, we continue by combining the like terms, these two in the middle, so we get 9x squared plus 30x plus 25. Again, we're just distributing or multiplying using FOIL. Again, you can just distribute every single time. Just make sure that you understand there are two of those. The biggest mistake on this is that students try to take this squared and apply it to both pieces here, and they get 9x squared, and then they get plus 25. Now notice you're missing the middle term, so the 30x here is gone. It's a completely different numerical value if you were to calculate using that expression. So make sure we understand that. Then if we move to something like the one you see on the right, again, as soon as I see it say squared, I could set this up as a minus 2b, again, multiplied by itself. So there's just two of them. When we multiply a times a, we end up with a squared. A times negative 2b, right? I have an a and a b involved there, would just be negative 2ab. Negative 2b times a, also negative 2ab. And then negative 2 times negative 2, negative 2b times negative 2b would be a positive 4b squared. Again, you have two like terms here in the middle, so if I have negative 2ab and negative 2ab, those can combine. So I would have a squared in front, negative 4ab in the middle when we add those, and then plus 4b on the end there. Now, one question I got asked in class a lot is, does it matter what order these are in for standard form? It doesn't. As far as the definition we made for standard form, because these actually all have the same degree. This one has a degree of 2, so yes, we think it gets to go first, but this one also has a degree of 2, and that middle one actually has two variables, so he has a degree of 2. So this one, they all have degrees of 2, so whatever form you put it in is just great. Okay. Again, multiplying through on these practice problems, right, we'd have 3x plus 4 and 3x plus 4. One thing that you'll notice on these is that those middle terms that we're combining are always identical. And so sometimes a shortcut that is used is we just know that when we multiply first times first, we're going to get 9x squared. When we multiply 3x times 4, we're going to get 12x and 12x again. So we just take 12x and we just double it. So we get 24x in the middle. And then 4x times 4x is 16. So that's kind of the pattern with this one. The way we write that would be, and I'm going to write this kind of up here at the top, if I ever have something and it's squared, right, it means there's two of them. And when I multiply that out, I get a squared in the front, and there's two of the middle terms, so whatever that a and b is, and then we get the b squared piece in the back. Now, there's not always a variable there. Maybe the b squared is like this 16 we have here because our b value is 4. So notice if I'm looking at that pattern, right, the a squared is like 3x squared was 9x squared. The 2ab, so here's my a and my b, that's 12x doubled. And then I have the 4 squared is 16. Again, if that pattern doesn't click with you at this point, that's okay. We'll use it later and talk more about it. Sometimes it makes more sense going the other direction. But if you just need to write two of them out, as we're doing on example B, that's fine, and then go ahead and FOIL that. So we get 25x squared. We get negative 10xy, negative 10xy, and positive 4y squared. Again, combine that like term in the middle. We get 25x squared minus 20xy plus 4y squared. Okay. I don't know if you've noticed this, but every time we multiply our binomials, we've been ending up with trinomials, right? Because we combine that middle term. Kind of cool to see. When we look at the next examples or the next pattern, notice that these also are just two binomials being multiplied together. However, instead of being the same, they're opposite operations. So one's plus, the other one is subtraction. And so we don't write that like x plus 2 squared because there's not two of the same. These are two different ones. This is the sum and difference pattern. So notice here, if I start to FOIL this, I get x squared. And if I multiply here, I get negative 2x. I continue multiplying. I get positive 2x, and then 2 times negative 2 is negative 4. As I simplify these middle terms and combine them, notice that negative 2x and positive 2x add to 0. So essentially, we don't have a middle term anymore, and we end up with x squared minus 4. Okay, and essentially, when these are identical binomials but opposite signs, that's exactly what's going to happen every time. I'm going to end up with p squared here. I'm going to get a positive 7p when I multiply that. I'm going to get a negative 7p. So those two are going to cancel each other out, which then leaves me with a negative 49. So if we can see this pattern, we understand this is a situation where we multiply a binomial and we end up with a binomial instead of that trinomial. Okay, same thing here. I'm going to get 4x squared. I'm going to end up with negative, and I'll write this one out, 6x, positive 6x, and 3 times negative 3 is negative 9. So again, those middle terms add to 0 because they're exactly opposite, and we get 4x squared minus 9. Okay, so I'm going to let you kind of describe that pattern, however it makes most sense to you, whether a binomial times that binomial, right, makes it a binomial, or the middle terms always cancel, something related to that. Then if we look at the sum and difference pattern, again, if they're identical but different signs, then we just end up with the first terms and the last terms because those middle terms canceled out. Looking down at C, if we're using that pattern, that would be like t squared. We know the middle ones cancel, so minus 25. It allows us to use kind of a shortcut. But if all else fails and I don't see the shortcut, we just multiply it all out. Again, using that shortcut, 9x squared, y times negative y is negative y squared. Okay. At this point, we've been through all of our operations. So what I want you to notice on this next spot is this is just, can we identify which operation is actually being done, and do we know kind of the differences when we do that? So if you look at E, right, we look between them, and these ones are sandwiched together, so this is implying that it's multiplication. That's really important because now I know I can start to FOIL this. And notice these are identical binomials but different signs. So this is one I can use the shortcut on. X times x is x squared. I know these two middle pieces will cancel, so I just go 2 times negative 2 is x squared minus 4. Moving to F, again, we look between these before we start multiplying. Now, a lot of students will just see parentheses and they start going like this, right? It gets messy really fast. This one is addition. There's an add sign between them, which means we just combine like terms. The exponents don't change unless we're multiplying. So we've got a negative 3x squared and a 5x squared combines to give us 8x squared. We've got a 4x and a 2x. Those add together to give us 6x. And we've got a 3 and a 1. So 3 plus 1 gives us the 4 on the end. Again, G, we look between them. Notice this one right here is subtraction, so a lot like addition, right? Combining like terms, we just need to make sure this negative applies to each piece over here. So that would be like negative 6y squared minus 4y because it was positive, and then a negative to that negative 2 would be a positive 2. So then I'm going to kind of ignore that because I fixed all the signs and combine like terms. So I've got a 3y squared here and negative 6y squared. When we combine that, we get negative 3y squared minus 4y, and we have 8 and 2, we get positive 10. And then h, again, this squared implies multiplication. So again, this just means that we have two of them, right? A 3x minus y and a 3x minus y. So again, if we multiply that through, we get 9x squared. We get negative 3xy, negative 3xy, and positive y squared. Combining those middle terms, we get negative 6xy plus y squared. Okay. The application problem on here, just relating this to the square of a binomial. Notice this Punnett square over here, all right, is a square. It has r and a w on the top, r and a w. This Punnett square is an example of what we call incomplete dominance, right? It's an area model that shows the possible results of crossing two pink snapdragons, each with one red gene and one white gene. Each parent snapdragon passes along only one gene for color to its offspring. So we can look at these results, right? If it gets red-red, red-white, all of those outcomes. The first part says, how can the square of a binomial be used to model this Punnett square's outcome? Well, this is essentially creating like our box method. So we've got RW here and RW here. And remember, every term in the binomial got its own row. So this is basically like r plus w, and this is r plus w. So we could write that as r plus w times r plus w. But again, because there's two of the same, generally we would just write that as r plus w squared. So we can use that square binomial. B says create a polynomial that includes the likelihood, or the chances, right? The probability there. Oh, that's spelled wrong. Of each outcome occurring. So essentially, if you look up here, R right here takes up half of this side, and white takes up half of this side. So we could say that we've essentially got 0.5 red plus 0.5 W. And if we square that, right, that's saying like 0.5 R plus 0.5 W times 0.5 R plus 0.5 W. And if I go ahead and multiply that, 0.5 times 0.5 is going to give me 0.25 R squared, plus I'm going to get 0.25 RW plus 0.25 RW plus 0.25 W squared. Those middle terms both have an RW, so we combine them and we get 0.25 R squared plus 0.5 RW plus 0.25 W squared. This right here would represent the polynomial related to the probability or likelihood. And it makes sense if you look at the box method, right? There's a fourth of a chance, or a 0.25 chance, that we get the double R. So if you look up here, that's 1 out of 4 boxes, right? 1/4 chance that one happens. Notice the pink is 2 of the boxes, so that's like a half a chance, 2 out of 4. So we've got 0.5 as our coefficient on the RW term. And then again, white is 1 out of the 4, so it's back to the 0.25. So just make sure we're really comfortable with multiplying out the polynomials, whether they're in this squared form or being able to identify when we're adding and subtracting.